today we will continue about talking about models with logs in the context of the multiple linear regression model. So remember now that we're talking about estimating nonlinear models in the context of our multiple linear regression model. We describe the general characteristics of nonlinear models being those that show curvature and where the marginal effects are not constant. And we say that there are two broad groups of nonlinear models that we're going to be covering in this class. So the first group were quadratic models, and the second group were models with logs. And we talk about three main types of models with logs used in economics. The first one is the one that we already talked about, which is a log-log model, which means that you have the log of the dependent variable and the log of the explanatory variable. So today we will be talking about two other models involving logs. One that's going to be the log level model, and finally we will talk about the level log models. Okay. So remember, previously in the log-log model, we have a model where we have the model of both the dependent variable and the explanatory variable. In the case of the log level model, we will see that what we have is the log of the dependent variable, and we have the explanatory variable x, without the log. In the case of the level log model, we will have just the dependent variable without any transformation, without taking the log, and we will have the log of the explanatory variable. Okay, so that's today's topic. Log level model and level log models. So just a reminder, remember the log-log model was a model that was very flexible. We were able to estimate different type of relationships. We talk about that it was very popular in economics because the coefficients could be interpreted as elasticities. And we also talk about the predictions of Y with log models. Okay, so now let's focus on log level models. Okay, so it's called log level model because it's a model where we have the log of the dependent variable, and then we just have the explanatory variable x. Okay, so this is what's log, and this is what the level refers to, plus an error term. Maybe a stable model. Okay, so that's the model that we're talking about when we refer to the log level model. In terms of the shapes that we can estimate, so we have y, we have x, so we have this model that the relationship between y and x is decreasing. Okay, that's called decreasing at an increasing rate. So this is the case where beta 1 is less than 0. We also have y and x, with just beta 1 equal to 0, it's just a line. And the other shape of the relationship is for a model that it's increasing at an increasing rate. Okay, so that's the type of models that we can estimate when we talk about this log level model, and of course here beta 1 is higher than 0. Okay, so let's say we estimate the model. How do we go about interpreting those coefficients, the beta naught and the beta 1? So interpretation. Okay, so this is the way that we're going to be interpreting that beta 1. So we will say that a 1 unit change in x changes y by approximately So make sure that you emphasize this is just an approximation. It's going to be by beta 1 times 100%. Okay, so when we're interpreting the coefficient, what we're looking is a 1 unit change in x, and we're looking how y changes in terms of percentage. And the percentage change is beta 1 times 100%. Now, why is that we call this approximation? Well, this is an approximation. This calculation of beta 1 times 100%, it works better, so this approximation. So the approximation works better when that beta 1, the beta 1 that you estimate that coefficient, is relatively small. And we say relatively small if it's between minus 0.10 and 0.10, negative 0.10 and positive 0.10. If, beta 1 happens to be outside that range, and, so that we can talk about the absolute value. So if the absolute value of beta 1 is higher than 0.10, it is better to use E. Remember, E is that constant that we had mentioned before. E to the beta 1 minus 1 times 100%. Okay? Now, remember, this is approximately equal to beta 1 times 100%, but only when that beta 1, the absolute value of beta 1, is less than 0.10. If that coefficient beta 1 is larger than 0.10, it's better to use this formula here. Okay? So let's look at an example. So let's look at the effect of education on wages. Okay, so, and that's an example that, we had talked about before. Remember, we were interested in looking what's the effect of education on wages. And before, I think the model that we had estimated was a linear model. Now let's explore the potential to use nonlinear model. Okay, so, of course, if I was in class, I would say, okay, we're going to be estimating this model. And remember that when we use a log level model, the type of relationships that we are kind of assuming implicitly is a relationship with an increase in x decreases y, which, as you know, doesn't make any sense in the case of the effect of education in wages, because we cannot say that higher education decreases wages. So, I guess the only reasonable model, that we're in a way are assuming is this model where we're, I guess that we're trying to estimate is a model where education increases wages. And as the curve can, as you can see in the curve, that effect, the effect of an additional unit of x in wages increases as you have a higher level of education. Okay, so remember that marginal effect, that effect of an additional year of education increases if you have at higher levels of education. Remember, that's kind of a nonlinear model is a model where we're estimating these non-constant marginal effects, which, I guess kind of makes sense. So later on we will see if in fact the model that we're estimating, looks like that. And again, that's going to depend on that design of that beta 1. Okay, so let's continue. But, again, when you are estimating these models, you need to have an idea of what are the type of relationships that you implicitly are assuming when you estimate the model. So I think that, we use the same data that we had used before. So we have data on wages. and those were dollars per hour. And we have data on education. And given by the number of years of education. And the estimated model is 0.5302 plus 0.0917 education. Okay, so we have 0.9349, 0.0179. So the R square 0.16 and 142. Depth statistic 26.22. And the p-value less than 0.01, which, that p-value for the statistic means that this model is useful for prediction. And, 16% of the variability in wages is explained by the model. So, I guess the model is useful for prediction. So, we can go ahead and see if we can interpret the coefficients. Now, I guess before I move forward, notice that I focus the interpretation. Here I focus interpretation on the beta 1 coefficient. Again, when we have these models with log as the dependent variable, the interpretation of the intercept. So here I should have said beta 1, and the beta naught, just for completeness. There is an interpretation for the beta naught, but we'll say that it is not very useful. Okay, so that's why we are focusing on the interpretation of the beta 1. Okay, so remember, we have this model of y, so we cannot say that beta naught, we can interpret as saying that beta naught is the value of the log of y when x is equal to 0, but it's kind of hard to think in terms of the log, so that's what we don't emphasize that interpretation, and we emphasize the interpretation of that beta 1 coefficient. Okay, so let's continue. Sorry for that digression. Okay, so beta 1, if we see kind of the way that we describe, so we said that the way to interpret beta 1, we said that 1 unit change in x changes y by approximately beta 1 100%. There is an extra by here. Okay, so if I was in class, I will ask you to think about it to help me with this interpretation. Okay, given the fact that we got 0.0917. Okay, so a key thing to remember here is that since we don't have education in logs, we're looking at the effect of an additional unit of education. Okay, so that's important to remember. So since we do not have an education, so we can talk about the effect of an additional unit of education. So we can say that an additional unit of education increases wages by approximately So remember, what we have to do is we have to multiply that coefficient times 100, and we interpret as 100%. 0.017 times 100%, which is equal to 91.17%. Okay, so that's interpretation. So an additional unit of education increases wages by approximately 9.17%. Okay, so now let's use that formula calculation. So remember, if you want to calculate the exact value, we'll say 0.e to the 0.0917. Okay, remember that's the beta 1 hat minus 1 times 100%. And if you were to do that calculation, that will give you 9.60%. So let me see if I have a calculator here, if I can find a calculator. To show you. Calculator. Okay, so let me see if I can open this up. And let me see if I need a scientific calculator. So what I'm talking about is this function e to the x. So e to the 0 is equal to 1. So let me see, how do I work this one? So I'll have to write 0.0917 e to the x, and that gives me 1.096 minus 1 times 100, and that gives me that 9.60% that I show you previously. Okay, so again, that's kind of what that e function here I'm talking about. Okay, so that's the way I did that calculation. So that actually you can see how that works. Now in terms of the shape, so remember we already know. So this is positive. So based on those two graphs that I showed you previously, that's kind of the type of relationship that we're estimating, which kind of makes sense. So you see, if you see at this graph, basically what this graph is showing you, that the effect of an additional year of education in terms of dollars per hour is smaller at the beginning. Okay, and again, that same one additional year of education becomes larger later on. Okay, now notice that we estimated in terms of percentage, and it kind of makes sense, because remember, like a 10% of, let's say for example, $1 is going to be smaller. The 10% of $1 is just 0.10 cents, and the 10% of $10 is going to be $1. Okay, so actually, both things are consistent. The fact that the marginal effects at the beginning are smaller and later are larger is consistent with having this constant percentage effect on wages as for an additional year of education. Okay, so that's very straightforward. The estimation of this log level model. Now let's look at the level log model. So now let's look at the level log model. So as you would expect, so this is a model where we have y equal to beta naught plus beta 1x, well, beta 1, sorry, that's the log of x. Okay, plus 0 terms. Of course, this is the level. I mean, y is just not, we're not calculating the log, and it's called level log because then we have the log of the explanatory variable. In terms of the shapes, kind of so we have this shape, beta 1 is less than 0, and then the other type of relationship that we can estimate is a relationship that is increasing but at a decreasing rate when beta 1 is larger than 0. Okay, so how do we go about interpreting the coefficients? Okay, so again, remember the focus is going to be on beta 1, because on beta 1, I mean, beta naught, again, we're going to say that that's the average value of y when the log of x is equal to 0, but again, the log of x being equal to 0, it might be meaningful or not meaningful, so we don't emphasize much the interpretation of beta naught. For completeness, we can say that's not very useful or meaningful, and we focus on the interpretation of that beta 1. Okay, so now, and so that hopefully you start to see a pattern. So now we have the log of x. So of course we're not going to be able to talk about like a one unit change in x. Since we're taking the log of x, we're going to be looking at the effect of a 1% change in x, and the change of that percentage change in x, okay, is going to be measured in terms of changes on y, on the actual units of y. Okay, so I'm going to write that down. So that beta 1, the way that we interpret the beta 1, we will say that a 1% change in x changes y by beta 1 over 100 units. Okay, so that's the way that we interpret. So notice here that we divided that beta 1 by 100 for the interpretation. So let's look at an example to see how we can apply that interpretation and also look at the shape that we estimate. So this comes from data from a project where they were looking at the effect of distance to a garbage incinerator on house prices. Okay, so we had several examples where we were looking at the effect of several things on house prices, and this is from our textbook, Goldrich's textbook. So the model that was estimated as a model where we have an intercept. So we have the house price and we have the log of distance. Okay. And the units are, well, house price are given in dollars. Okay. And distance really doesn't matter because we're going to be looking at the effect of a 1% change. Here I don't have it in front of me. I'll have to go back to the original file where I estimated the model. In any case, I mean, we don't need those units since again, we're going to be looking at a 1% change in x. Actually, the units could be any units, but we need the units of house prices for our purposes. So the estimated model minus 2,271 as 34,759. So this is the log of distance and standard errors, and I'm using the equation form to present the results. R squared 0.13 and 142, F 20.25, and the p-value less than 0.01. Okay. Okay, again, so in terms of interpretation, since we have the log of distance, and again, we go back, we're looking at 1% change in x, and we see how that changes y, and the way that we're going to be measuring the change in y is in beta 1 divided by 100 units of y. So given that, then we will say that a 1% increase in distance from, oh, I think I touched something. Let me see, a 1% increase in distance from the incinerator. Increases house prices by, so again, this is going to be that coefficient divided by 100. 34,759 divided by 100. So this is going to be $347.59. So a 1% increase in distance from the incinerator increases house prices by $347.59. In terms of the shape, let's see if it kind of makes sense. The model that we estimated, so house price, distance, so based on those graphs that I showed you previously, so that's the model. So, at the beginning, the effect of distance are very large. Okay, so if we were to look at the effect here, okay, and later on, the effects are going to become smaller, which, I mean, is kind of what you will expect. Yeah. So with that, I think that's the three type of models. Just to summarize interpretations, something for you to have in mind when you are trying to interpret. It's good to have in mind, well, and I'm also going to write, so level log model. And for reference, I'm going to write the level. Okay, so when we have a log model, remember the interpretation of the beta 1, we talk about a 1% change in X, and we look at the change in Y in terms of percentage. Okay, when we have the log level model, since we have level model, we will look at the 1 unit change in X, and the change in Y is expressed in percentage. Okay, remember that you have to multiply it times 100, and I'm not going to write that down, just to give you the intuition. If we have a level log model, we will look at the 1% change in X, and the change in Y will be measured in units. Okay, if we have a level model, remember that we have a 1 unit change in X, and the change in Y is also expressed in units. Okay, so have that in mind, kind of like a general intuition when you are interpreting these coefficients. This is good to have in mind. And of course, for the log level model, that coefficient needs to be multiplied times 100% if it's small. If not, you need to use the formula. And for the level log model, that beta 1 coefficient will have to divide it by 100. But that's a detail that you need to memorize. But in terms of the intuition, something that you very fast you can remember the intuition. This is the way to think about these interpretations. Okay, well, thank you. That's all I have for you today.